we're going to talk about how to numerically compare two numerical variables. So for numerical variables, we have the speed, we have this converted speed into meters per second, we have age. Now we have talked about how plate location is not numerical. It's actually a categorical variable, but there are numbers there and I want to show you something. So I'm going to actually include that data right now. So let's copy D, E, F, and G. And let's copy it onto the numerical versus numerical tab. Okay, now you don't have this, which is fine. Notice how this had an issue with the reference. Let's go back to the raw data. See, the thing with the age is the thing with the age is that they are random numbers. And so you've probably been noticing as we click on different things, the ages change. And I don't want that to be the case. So even though like this was randomly determined, I now want these numbers to not be randomly determined. I want them to be fixed. Like we've already randomly determined them, but I don't want them to keep changing. The easiest way to do that is to click on it and copy it. So I'm going to do Control C, and then I'm going to do Control V for paste. Oops, let me undo that. Let's Control C, and then Control V, I want to paste, but I want to paste as values. So now they're pasted as values, and so now you see there's no formula left anymore. It's just the values. And so now I can copy and paste that column, and I keep the numbers. So okay, so now we have 4 numerical variables. Well, this isn't numerical, it's categorical, but we are going to abuse that for a second. To numerically compare the strength of 2 numerical variables, it is very common to make something called a scatter plot. So that is a graph where one variable is on one axis, the other variable is on the y-axis. And we want to measure how easy it is to predict the y variable from the x. Like here, it's perfectly easy because there's like a linear formula. Here, it's not so perfectly easy, but it's still, you know, we could predict it within a little bit. Whereas here, like knowing what the x is doesn't tell me what the y is at all. And so this is called the correlation between 2 variables. And so if someone says correlation, 2 variables are correlated, what that means is that both variables are numerical, and it's talking about the strength of predicting one from the other. And I'm going to add a little bit to that in a second. We abuse the word correlation, which you're not going to abuse in this class anymore. A lot of people will say something like, the number of drownings and the type of weather day are correlated. Well, they might be associated, but correlated is that there's 2 numerical variables, and the type of weather day is not a numerical variable. So correlation is going to be a number that represents the strength between 2 variables. For perfect, like this, the correlation is 1. And often when we talk about correlation, we use the value little r. Oh, isn't that fun? Okay. And so like this right here would be an r of 1. Where'd it go? Okay. Now, if you had something that looked like this, so instead of going over and up perfectly, it went over and down perfectly. So it had this shape, but it was perfect. Then it would be r equals -1. That's not perfect, but it's not bad. So the highest perfect positive correlation is +1. The most perfect negative correlation, and negative doesn't mean bad, it means as one variable gets bigger, the other one gets smaller. The perfect correlation would be -1. So this one is like sort of moderate. I would say that this is an r equals -0.8. Okay, now if that's the case, then we're going to say that this one is an r equals +0.8. Maybe this is a 0.3, and this is about 0. Knowing the value of 1 of x does not tell me about y. Now, the same actually is true here, because now, are these two variables associated? Yes. This is sort of like if you fertilize a crop and you look at output. When you add fertilizer, you get more output until you start to over-fertilize and kill everything. The thing is, the correlation here would be about 0 as well, because correlation isn't just measuring whether or not there is an association, it is measuring linear association. So correlation measures linear association. So two variables can be associated, but if they're not associated linearly, then that still has a very bad correlation. The weakest correlation is 0. And so correlation is somewhere between a -1 and a +1. Okay, that said, let's find the correlation between our numerical variables. Now, first of all, imagine if you graphed, this is a correlation matrix. We're going to find all these correlations. Imagine if you graphed x-axis plate location, y-axis plate location. So x is 11, y is 11. X is 1, y is 1. X is 12, y is 12. It's a perfect line. So if you graph a variable against itself, you're going to get 1. So all of these on the diagonal correlations are 1. Now, here it's going to be the correlation. Let's do speed and age. So I'm going to do speed in miles per hour and age. So I'm going to do the correlation between our speed, that's column B, and age, column D. Okay, so it's positive, which we expect. As age increases, so doesn't speed. It's not perfect, which is definitely, we wouldn't expect it to be perfect, but it is reasonably strong. Now, I should have said, I put 1 in there. I could have done the correlation of what is speed, B with B, and we get 1. Okay, now notice, this is the speed and age. If we go in the matrix to age and speed, so this is the correlation. Age is column D, the speed is column B. We get the same numbers, and we should, because correlation is measuring how two variables are linearly associated, and so which one is the x or y, they're going to still have the same amount of linear strength, which means I only have to fill in half of this because the other half will be the mirror image. All right, let me take this. I'm going to bring this down everything to, I think, 2 decimal points. Okay. Now, here's an interesting one. So we're just going to do the upper part of this matrix. Let's look at the speed in meters per second and the speed in miles per hour. So right here. So that's the correlation, miles per hour is B, meters per second is C. Imagine a graph where on the x-axis you have miles per hour and on the y-axis you have meters per second. And don't you think it would be near perfect because there's like a linear relationship? Okay, and we are getting 1. Now let's look at this one, speed and plate location. We talked about how plate location is categorical because we just assigned numbers here. It's not like 2 is bigger than 1 or 8 is 7 bigger than 1. These are just categories that we gave a name. And so in some sense, our assignment of number to region was like sort of a random choice. Accordingly, I would expect that this is a really bad correlation because as you change the plate location, what happens to the speed? Well, this is a categorical random assignment. Let's look at the answer. Plate location is A, speed in miles per hour is B. Okay, it's close to 0. Basically, no correlation. Knowing something about plate location does not tell us any information about speed, and that we would expect. The same thing is going to go here for meters per second. Now, what and age. So like this is all just blah. We shouldn't even be doing this because plate location is actually not a numeric variable. I just wanted to give an example of something that I know would be really bad. Okay. So let's make this new variable age to retirement. All right. Let me first look. What's the maximum of the ages for these pitchers? The maximum of D is 31 years old. Okay. So suppose that we say a pitcher retires at age 32. Then if they're 31, they have 1 year to retirement. In other words, 32 minus 31. So we are going to have the age of retirement be 32 minus their actual age. So let's copy all that down. Okay, so now here, let's make the correlation of the age to retirement and the miles per hour. And we're going to get negative 6.7. So we should expect that we get the same absolute value of number because these two are linearly related. Like one of them is just 32 minus the other. So their strength is the same, but their sign is different because here, as age increases, speed increases. But as age to retirement increases, meaning the player is getting younger, so as that happens, we expect the speed to decrease because younger players will pitch slower. Okay, and I think that, oh, we should say, what about the age and age to retirement? Guess the value. Should be 1. Or negative 1 because it's a perfect line. Age to retirement is 32 minus age. So it's a perfect line, but as one variable gets bigger, the other gets smaller. So the correlation is negative. In the next video, we'll add some graphs to this.